This is a review video for some of the material for week 2 in the course Chem 099. There were a couple of important words in that introduction, and I bolded them on the video just to make sure we all are clear about this. This video is just a quick review. This is not the only thing you should use as you learn the material in week 2 and study for sapling and the Canvas quiz and exams. It also only covers some of the material for week 2. The way I chose the material to be in this video are the ideas and concepts that I get the most questions about. So the purpose of this video is for you to read through the chapter, watch the lecture videos provided to you by the textbook and the textbook authors. If you have the e-text, then you can get to those lecture videos by just clicking on the links for them as you read your online textbook. If you have a paper copy of the textbook, you can get to these lecture videos from sapling. So when you go to complete your week 2 sapling, right below where the resources are for the week 2 sapling, it says week 2 resources. You click that, and then there are lecture videos as well as example videos listed right there. So you should not watch this video until you have already read and watched the lecture videos from Chapter 2, completed your chapter notes, and then if you still have questions or concerns, this is a great video to watch to help you with this. But I don't want anyone to think that this is the only thing you need in order to learn all of the material you need to learn for week 2. So hopefully that has been clear. So again, the topics that I chose to cover in this video, I'm just going to review them, do a couple examples, and I chose these topics based on the ones that I get a lot of questions from for students. So first off is how to determine the number of significant figures or significant digits in a measurement. So there are 4 rules in our textbook to do this. So I'm going to review those rules and then we'll practice a few. So the first rule. All non-zero digits are significant, and all zeros between non-zero digits are significant. So, backing up, the point of significant figures is when someone makes a measurement, we're trying to decide which numbers that they wrote down are significant in terms of how certain are you of your measurement. So, did they write that digit down deliberately? Or is that just there as a placeholder, or what is going on? So looking back at this, all non-zero digits, that means numbers 1 through 9. Any number that is not a 0 is automatically significant. 1, 2, 3, 4, 5, 6, 7, 8, 9. Significant. No ifs, ands, or buts. It is automatically significant. Zeros are the only ones that give us trouble. So in this rule, any 0 between non-zero digits is automatically significant. So in the example right below there, I have the measurement $507. I have the 0 there highlighted in red because that is a 0. So we're looking at that, trying to decide is it significant or not. The 5 and the 7 are automatically significant because they're not zeros. They're any other number other than 0. So the way I think of this rule with the zeros between non-zero digits are significant, if this was my bank account balance, if I had $507 in my bank account, I would not want my bank to think, hey, that 0 is not important. You now have $57 because that 0 is important. It is very significant. That 0 is there on purpose. So the $507 shown there, in that measurement, the 0 is significant, so that has 3 significant figures, the 5, the 0, and the 7. Rule 2. If a decimal point is present, zeros to the right of the last non-zero digit are significant. Okay, I know these sound crazy, but let's break it down. It's fine. A decimal point. When you write down a number, if you see a period, it looks just like a period, but it's called a decimal point when we're looking at it in a measurement. If you can see that decimal point, that period, if it's visible to your eyeballs when you look at the number, okay, then we can follow this rule. Zeros to the right of the last non-zero digit. So, zeros at the end of the number. Zeros after all of the other numbers. So all the other numbers are written, and then there's zeros at the end of the number. If you can see the decimal point, zeros at the end are significant. So in this example, 15.90, the 1, the 5, the 9, based on rule 1, they are automatically significant. The only one we're not sure about is that 0, so the 0 that I've colored red. So based on rule 2, if a decimal point is present, when I look at that number, there's a decimal point right between the 5 and the 9. I can see it with my eyeballs. So 15.90, the decimal point is present. Great. So that means zeros to the right, or zeros at the end of the number, are significant. So that 0 that I have in red, it is significant because it's at the end of the number and I can see a decimal point. Rule 3. Zeros to the left of the non-zero numbers are never significant. So zeros at the beginning of the number. Any number that starts out with 0. So numbers less than 1. So like 0.0045. So those zeros are on the left of the number, at the beginning of the number. So according to this, zeros to the left are never significant. What do you think about the 4 and the 5? Well, based on rule 1, 4 and 5 are not 0, so they are automatically significant. So 0.0045 has 2 significant figures. Just a reminder, rule 2 is only about zeros at the end or the right of the number. Rule 3 is about zeros at the beginning or the left of the number, so don't confuse those two. Last rule, rule 4, my least favorite rule from our textbook. It's a little bit ambiguous, so I'm going to change the rule a little bit. It says if there are no decimal point present, so you cannot see the decimal point, like that you cannot see the period, zeros to the right at the end of the last non-zero digit may or may not be significant. So I don't like the wishy-washy of this, so I'm making a hard and fast rule. If you have a number that you do not see a visible decimal point, the period, you can't see it in the number, and you have zeros at the end, they're not significant. So this number, 560. Well, I know right off the bat, the 5 and the 6 are significant. The only one I'm not sure about is the 0. So when I look at that number, I do not see a visible decimal point. I don't see a period in that number. So there is no decimal point present. So according to my rule here, zeros at the end, zeros at the right, are not significant. So 560, the way it's written right there, only has 2 significant figures. And you might be like, well, what's the deal with that? If I took away that 0, it would become 56. You're absolutely right, but we could write that number in scientific notation and take away the 0. 5.6 times 10 to the first is the same thing as 560. I took away the 0, and the number stays the same. That is not true for rule 1 when zeros are in between. If I take away that number, it can't be replaced by anything else. You're not going to see situations with rule 4 very often because it's so wishy-washy. Mostly rule 1, 2, and 3. So let's practice these. So I've got 5 measurements here. We're just going to figure out how many significant figures or significant digits they have. Significant figures and significant digits are the same thing. It's 2 ways to say the exact same thing. So the measurement, 21 grams. Well, the 2 and a 1, they're both non-zero digits, so they're numbers that are not 0, automatically significant. So this has 2 significant digits or significant figures. Wonderful. Second one, 21.0. So I know the 2 and the 1 are significant. It's the 0 that we have to stop and think about. So I see a decimal point and the 0 is at the end. Those are the types of things we're looking for. Where is the 0? And do I see a decimal point? So I see a decimal point and the 0 is at the right, at the end. So I need to look at rule 2. Rule 2 says, if you can see a visible decimal point, zeros to the right, to the end of the number, are significant. So I see a decimal point, the 0's at the end, it is significant. So the 2 is significant, the 1 is significant, and the 0 is significant, making 3 significant figures total in that number. 21.03. The 2 and the 1 and the 3 I know are significant automatically. It's the 0 I'm not sure about. Well, in this case, the 0 is not at the left or the right. The 0 is in the middle. If it's in the middle, it's always significant. So this has 4 significant figures or significant digits. My next measurement, 0.021 grams. So the 2 things I'm looking for. Where are the zeros? Are they at the beginning, or the end, or the middle? In this case, they're at the beginning. They're on the left. And can I see the decimal point? Well, it turns out zeros on the left, it doesn't even matter if you see a decimal point. They're never significant. Because I could write this in scientific notation as 2.1 times 10 to the negative second. If you're going, I don't know what scientific notation is, that's something for you to look up. It's in Chapter 2 in this week. So, based on our rules, Rule 3, zeros to the left, zeros at the beginning, are never significant. So the 2 first zeros we see are not significant. The 2 and the 1 are, so that's 2 significant figures or significant digits. Our last measurement, 0.02100. I put lots of zeros in here. So I have zeros at the beginning on the left. I have zeros at the end on the right, and I can see a decimal point. So we're going to look at these zeros, two different situations. So let's look at the left ones first. So the 0.0 before the 2. There's zeros to the left. Zeros to the left are never significant. So I can go ahead and say that 0.0, not significant. The 2 and the 1 are significant. Great. And then I have to deal with the zeros at the end, at the right. With that rule, we need to look to see if we have a visible decimal point. Do you think you can see the decimal place, the decimal point in this? Hoping you said yes, because we can see it right there between the first 2 zeros. So I can see the decimal place with my eyes. I see it. That means zeros at the end of the number are significant. So the 2 is significant, the 1 is significant, and the 2 zeros that come at the end are also significant, making this having 4 significant figures or significant digits. This just takes a little bit of practice. I know it seems weird, but I promise it'll be fine. So what we're going to do next, now that we know how to figure out how many significant digits or significant figures a measurement has, we're going to start doing math with those measurements, adding them together, subtracting them, multiplying or dividing them. So we need to talk about, once we're done doing addition, subtraction, multiplication, or division, what should our answer look like in terms of how many places it has, how many numbers we get to keep. So there are 2 different sets of rules for this. When you add or subtract, there's a set of rules. When you multiply or divide, there's a set of rules. So we're going to talk through those 2 sets of rules. So we're going to start with adding and subtracting. So just before you freak out about anything, we're not changing how you add or subtract in chemistry. The way you learned how to add or subtract, same. Your calculator works the same way. The way you learned how to do it in, elementary school, middle school, high school, college, whatever, adding and subtracting hasn't changed. All we're learning is how many of the digits of our answer do we get to keep? So like what you do in your calculator, how many of those numbers do you actually use for your answer? That's all we're figuring out. So the rule for addition and subtraction, it's all about the number of places after the decimal point. So we've talked about the decimal point, the thing that looks like a period, right? So when we're adding and subtracting numbers, we'll do our math. We'll go ahead and add them and subtract them, not change how addition and subtraction works. But in order to figure out how much of our answer we get to keep, we're going to look at the numbers that we're adding or subtracting. So we're going to look at them one at a time. We're going to look at the first number. We're going to find the decimal point in that number. And we're going to count how many places after the decimal place, so to the right, does it have. And we're going to do that for the second number that we're adding or subtracting. Whichever of those 2 numbers. So let's say the first number has 3 places to the right of the decimal point, and my second number has 2 places to the right of the decimal point. So 3 places versus 2 places. We look for the smaller number, so 3 or 2. 2 is smaller. So our answer gets to have 2 places to the right of the decimal point. So let's do an example. So here's it's a word problem, but I promise it's not a scary one. If we placed 25.0 milliliters of water in a beaker, so I poured 25.0 milliliters into a beaker, then I added 1.290 milliliters on top of it. I want to know what is the total amount, the total volume of water in the beaker. So we need to add these 2 numbers together. So one way to help you with this decimal place thing, back in elementary school when you were learning to add and subtract for the first time, you were given addition tables, like entire pages filled with numbers with one number plus another number, and they were set up one on top, one on the bottom, a plus sign and a line below it. So it looks kind of like that. Let's set up our numbers that way when we do our addition and subtraction. The thing you have to be careful with is to keep your decimal place, your decimal point, in line. So wherever you put the decimal place on the first number, the second number you need to line it up so the decimal place is right below it. So I'm going to take 25.0 plus 1.290. This is what I get. Again, I didn't change how math works. Okay. Following the rule, we would look at the first number and count how many places to the right of the decimal point. So 25.0, 1 place to the right, 1 place after the decimal place. 1.290, so 290. That's 3 numbers after the decimal point. So the first measurement has 1, the second one has 3. So which number is smaller versus 1 versus 3? 1. So our answer should only have 1 place to the right of the decimal point. The number we have written there has more than that. So that means we need to round it so it stops at 1 place after. A way to visualize this, I just drew a red line after the number that ended first. I was looking at the 2 numbers I'm adding together. I just drew a line after the one that stopped first. that shows me where I need to stop with my measurement. So 26.2, and there's a red line, so that's like stop. We do have to remember how rounding works though. So 26.2, and that 2 is followed by a 9, so I need to round that up to 26.3. So the first number we added, 1 place to the right of the decimal point. The second number we added, 3 places to the right of the decimal point. So my answer has 1 place to the right of the decimal point. That line is just helping you visualize that. We're going to do 2 more examples before we move on to multiplication and division. So with these, I didn't even do a story problem. I just went ahead and set up the numbers. So I'm going to take the number 1.230 grams minus 0.22 grams. So I would just take my calculator and do the math. 1.010 is what my calculator says. Great. So to figure out how many of those digits that I get to keep, we look at the top number, 1.230. There are 3 places to the right to the end after the decimal point. 0.22. There's 2 numbers after the decimal point. So the first one is 3, the second one is 2, so my answer gets to keep 2 after the decimal point. So there's me visualizing where it cuts off, 1.01 grams. So let's do the second one. 502.2 plus 20.50. 502.2 has 1 place after the decimal point. 20.50 has 2 places after the decimal point. When I add them together, that's what I get. So 1 place after, 2 places after, my answer needs to have 1 place after. So 522.7 seconds. So now let's talk multiplication and division. So with multiplication and division, the rules are a little bit different. Okay, we're going to not be looking at decimal places. We're going to be looking at the number of significant digits. So we're going to take, let's say I'm taking 2 numbers and I'm multiplying them. I'm going to take the 2 numbers and multiply them. Again, don't change how you multiply or divide. Chemistry's math is not any different. It's just how many digits we get to keep from our calculator. So I'm going to take the first number that I'm going to multiply, count how many significant figures it has. Second number I'm going to multiply, count how many significant figures it has, then plug them into my calculator, multiply the 2 numbers. My answer is going to have the same number of significant figures or significant digits as the number that I multiplied that had the fewest. So let's look at that. So this example, 6.34 centimeters multiplied by 13.24 centimeters. And I typed that into my calculator, and so that 83.9416, that's just what came out of my calculator. Okay, wonderful. To follow this rule, we need to look at both measurements, count how many significant figures they have, and then decide how many significant figures our answer should have. So 6.34, that has 3 significant figures. 13.24 has 4 significant figures. So 3 sig figs versus 4 sig figs. Our answer has whichever of those is the fewest. So 3 versus 4, which one's smaller? 3. So 83.9416, I only get to keep 3 of those digits that are significant. So 83.9. The units went from centimeters to centimeters squared because I took centimeters times centimeters. Centimeters times centimeters is centimeters squared. Let's do 2 more examples of this. So 15.2 times 0.2005. So let's count the number of significant figures in each of those numbers. So 15.2 has 3 significant figures. 0.2005 has 4 significant figures. The 0 to the left is not significant. The zeros between the 2 and the 5 are. So it's 3 significant figures, 4 significant figures. Before I even grab my calculator, I know that my answer needs to have 3 significant figures, because 3 versus 4, 3 is smaller. So I grab my calculator, 15.2 times 0.2005. That's the whole thing that comes up on my calculator. Great, but now I need to make sure it only has 3 significant figures. So I'm going to keep the 3 and the 0 and the 4, but I'm going to have to round the 4 up to a 5, so my final answer will be 3.05. Now we're going to do one that's division. It doesn't change how it works, it just changes which buttons you push in your calculator. So 0.566 divided by 1.8. So 0.566 has 3 significant figures. The 0 to the left is not significant. 1.8 has 2 significant figures. So what do you think? How many significant figures should our answer have? Well, 2. 3 versus 2, it's the smaller number, so 2. So 2 significant figures, but this is what my calculator says. So I need to round this to 2 significant figures. 0.31. Don't think that has 3 significant figures. Remember, zeros to the left are not significant. The 3 and the 1 are significant, but the 0 is not. So just a reminder, when you're doing addition and subtraction, you're paying attention to the decimal point in terms of what your answer should look like. When you're doing multiplication and division, it's all about the number of significant figures in terms of what your answer should look like. So the last big topic we have to talk about is doing dimensional analysis, which is converting units. But before we can do that, we need to talk about unit factors. Unit factors are just a relationship between two different units. A lot of unit factors you just know off the top of your head just by living life. So like this one, you know that $1 is equal to 100 pennies. If someone said, how many pennies does it take to get to $1? You could say 100 pennies. So instead of writing it as a sentence, I just wrote it with an equal sign between them. $1 equals 100 pennies. That's great, but in order to do math with these, it's what we're going to have to do. I want to take this relationship and write it as an actual unit factor, which means make it look like a fraction. Okay, so I'm going to take $1 divided by 100 pennies, which I could also say 100 pennies divided by $1, and I'm saying they're equal to each other. That one statement, $1 equals 100 pennies, I can write it either way. Now, I know if you look at this and you think, well, 1 divided by 100, hey Beth, that's not the same thing as 100 divided by 1. You'd be right if we were just looking at the numbers. Remember, this is not just saying 1 equals 100. It's saying $1 equals 100 pennies. Those two things really are equal to each other. So we could write it either way and it's fine. Now, depending on the situation, one of these is going to be more useful to us than the other. We'll get there in a minute. Okay, but let's do another unit factor first. So this is another one I think you know. 1 day equals 24 hours. So to write that as a fraction, I can either write 1 day on top and 24 hours on the bottom, or 24 hours on top and 1 day on the bottom. I can write both of those coming from that same statement. Okay, so there's lots of unit factors that exist. Most of them I will give to you. So things like if I wanted you to convert between centimeters and inches, I'm not going to assume you have that memorized. I do have some assumptions on like if you know how many hours are in a day, I'm going to make an assumption on that, but I will probably even give you that information. There are 4 unit factors that you have to memorize before we take an exam in this course. And these are 4 of the metric unit factors. In your textbook, there are more than 4. These are the 4 you have to memorize. So what you need to memorize, the name of the prefix, the symbol of the prefix, and the unit factor that goes with it. So the 4 prefixes, kilo, deci, centi, and milli, and their symbols, lowercase k, lowercase d, lowercase c, lowercase m. Make sure you know which one goes with which. And then there are the unit factors that go between them. So in this table, I used meters as an example unit, but the wonderful thing about the metric system is the prefix always works the same way, even if you change the unit. So like for the kilo row, it says 1 kilometer equals 1,000 meters. 1 kilo hour equals 1,000 hours. 1 kilosecond equals 1,000 seconds. 1 kiloliter equals 1,000 liters. 1 kilogram equals 1,000 grams. It's wonderful that that relationship stays the same. The kilo always means there's one of those kilo things and 1,000 of the other things. So you will have to have that memorized. For deci, centi, and milli, in that unit factor of the prefix box, there are 2 different unit factors there. You have to choose one of those 2 to memorize. For me, the second one makes the most sense. I don't like the decimal version. So decimeters are smaller than a meter. So it takes 10 decimeters put together before you get to 1 meter. So that makes more sense to me. 10 decimeters makes up 1 meter. Then 1 decimeter is 0.1 meters or 1/10 of a meter. They mean the same thing. It's just whichever way you like better. So I just happen to like the second unit factor better. So I went ahead and took that table and rewrote it, taking out the one with the decimals in it. So that's going to be the table that I use. Again, if the way that I do this, if you don't like my choices here, you could go back up to the first table and use the one with the decimals. Either way, you need to memorize the name of the prefix, the symbol of the prefix, and the unit factor that goes with it. So I just took that second table and plopped it up here because that's the one I'm going to use. Let's practice taking these unit factors and write them as the fractions. Okay, so I'm going to start with the kilometers. We're going to start with the top one. So it says 1 kilometer equals 1,000 meters. So I could write that 1 kilometer equals 1,000 meters, or 1,000 meters equals 1 kilometer. Again, the great thing about these metric prefixes, 1 kiloliter equals 1,000 liters, 1,000 liters equals 1 kiloliter. All that I changed was instead of using the unit meters, I used liters. But if you notice, nothing else changed about it. So now let's do the milli. Let's go to the bottom. But I'm going to do, instead of millimeters, I'm going to do milliliters. So 1,000 milliliters in 1 liter and 1,000 milliliters. Either one of these, both of these are true. Okay, and then let's do deci, but I'm going to do grams instead. So instead of 10 decimeters equals 1 meter, I'm going to say 10 decigrams equals 1 gram. 10 decigrams over 1 gram over 10 decigrams. So these 4 metric prefixes, make sure they're memorized. You could do all 3 columns in this table. So now we're going to do dimensional analysis. Dimensional analysis is just a fancy way of saying taking a measurement and converting it to another unit. So if you were timing, you were baking something in the oven and the cookbook said it needs to be 1.3 hours. You're like, great, but I want to know how many minutes that is. To do that math, that's you just doing dimensional analysis. Dimensional analysis, taking a number and converting it to another unit. So with dimensional analysis, when I read these problems, I have kind of a 3-step process that I do. So I'm going to teach you that 3-step process. So step 1, we'll read the problem. Great. After you read the problem, figure out what unit you need for the answer. What unit are they asking you to turn it into? So that's the first thing I want you to figure out once you read the problem. Next, go back and look at the problem and figure out what was the thing that you're starting with. What is the number that you have that you need to turn into another unit? And then the third is, what is the unit factor? What's the relationship between the unit that you need for your answer and the unit that you're starting with? A lot of times that unit factor is going to be given to you in the problem. The exceptions to that are if it's a kilo, deci, centi, or milli, then I'm just going to assume you have memorized those metric prefixes and you can use them. So when I answer those 3 questions, I actually take my notebook paper and my answer to step 1, what unit do you want in your answer? I write that on the right-hand side of my paper. And then the answer to step 2, what was the number that you're given? What are you starting with? I write that on the left-hand side of my paper. And then the unit factor goes in the middle. So let's do a couple examples here. So I want us to find the number of hours in 2.45 days. So step 1, read the question, figure out what unit we want our answer in. So I think the answer needs to be in hours. Find the number of hours in 2.45 days. So hours, great. Step 2, what's the measurement that we're starting with? So I decided it's 2.45 days. And then step 3, what is the unit factor, the relationship between the hours and the days? So this one wasn't given in the problem, but because I assumed we would know it, but 24 hours are in 1 day, or 1 day is 24 hours. We can write that either way. Now, we talked about how you can take one relationship and write it as 2 different fractions. One's on top and one's on the bottom. So this is how we choose which one to use in this situation. So the desired unit, that's going to be your answer to step 1. So in this case, hours. What I want my answer to be is hours. The number that I'm starting with, that's the unit for step 2. So in this case, days. So I'm starting with the unit days on the left and I'm ending with the unit hours on the right. So the version of the fraction that I need to get between hours and days, you're always going to take the unit that you're starting with, and that's going to go on the bottom of the fraction. The unit that you want for your answer goes on the top of the fraction. So that's our unit factor. That's how we figured out which of those 2 fractions to set up. So we're going to do this actual problem with the real units here in just a second, but that's just something for you to refer back to if you're not sure how to set up your unit factor. Okay. Oh, and they will always cancel out. That's the point, is to cancel out the unit we start with and the unit that we end with. So you'll notice I always actually cross them out. So for that problem, we were solving for hours. We're starting with 2.45 days. And then I need to set up the unit factor. We know that 1 day equals 24 hours. But I've got to decide where to put the days and where to put the hours. So since I'm starting with days, day needs to go on the bottom and hours need to go on the top, so I can cross out the days. So that unit is gone. So day is gone. Now I need to take my calculator because I actually have to do this math. I'm going to take the number 2.45 times 24 divided by 1. You can skip the dividing by 1 step if you want because it's not going to change your answer. So 2.45 times 24, this is what my calculator gives me, 58.8 hours. So 2.45 days is the same thing as 58.8 hours. All we did was just convert the unit. We're going to do a couple of more. So in this one, if a bar of silver weighs 0.890 troy ounces, what is the mass of silver in grams? You don't have to know what a troy ounce is in order to do these problems. So don't ever freak out if you see a unit and you've never heard of it before. Just follow our 3 steps. Okay. Notice that below the question in parentheses it says given, 1 troy ounce equals 31.1 grams. That's me telling you the unit factor between troy ounces and grams. I will give you all of them other than kilo, deci, centi, and milli, and that's not applicable in this problem. So let's read the question again, figure out what unit we want for our answer. If a bar of silver weighs 0.890 troy ounces, what is the mass of silver in grams? So I'm going to say my answer needs to be in grams. So I'm going to write a G for grams. That was step 1. Step 2. What are the thing that we're starting with? What is the unit and the number that we have to convert? So 0.890 troy ounces. So I'm going to put that there on the left. Step 3, we have to set up our unit factor. So that's going to be the 1 troy ounce equals 31.1 grams, but we have to decide what to put on top and what to put on the bottom. So since I'm starting with troy ounces, that's the unit on the left. That's the unit that needs to go on the bottom of my unit factor. So I'm going to put 1 troy ounce on the bottom and 31.1 grams on the top. And I'm doing that so I can cancel out troy ounces. So in my calculator, I'm going to take 0.890 times 31.1 divided by 1. When I did that, I get 27.679 grams. That's wonderful, but something that we need to think about here, we just practiced how to figure out what our final answer should look like if we're either adding or subtracting or multiplying and dividing. So we need to actually do that here. So 0.890, that has 3 significant figures. 31.1 has 3 significant figures, so our answer should have 3 significant figures. So my answer is actually 27.7 grams. Let's do one where we have to use our metric prefixes that we have memorized. So the question, convert the length measurement of a lab sample of 45.9 centimeters to meters. Notice it wasn't given in the question, the relationship between centimeters and meters, because we're supposed to memorize that. So looking back at that table, there are 100 centimeters in 1 meter. So I italicized that and bolded it just to remind you that's not going to be in the question. You have to have that memorized. But let's start the problem the same way. Read the question, figure out what unit we want, what unit we're starting with, and put our unit factor there. So when I read the question, I want my answer in meters, and I'm starting with 45.9 centimeters. And then I need to take that 100 centimeters equals 1 meter and set it up so that way my centimeters are on the bottom and the meters are on the top, so that way the centimeters can cancel. So now I'm going to take my calculator and take 49.9 times 1 divided by 100. My calculator gives me an answer of 0.459 meters. So there were a few examples of dimensional analysis converting units. So just a reminder, the things you have to memorize before you take an exam in this course, you have to memorize the relationship between the temperature unit Kelvin and the temperature unit degrees Celsius. So that equation is you take the temperature in degrees Celsius and you add the number 273 to it, and you've now converted to Kelvin. You also need to memorize the density equation, which density equals mass divided by volume. Usually that is mass in grams divided by volume in milliliters. And then you need to memorize the 4 metric prefixes that I've discussed several times in this video. The name, the symbol, and then the metric prefix. And again, for the last 3, you can choose either the prefix on the left of the or on the right of the or, whichever one works, but you need to know that. I also just copied over the Chapter 2 objectives. Chapter 2 is the only chapter we're doing in week 2. So there are 4 objectives that I made red on this. I just wanted to point out that those 4 objectives were not covered in this video at all. You still have to know those 4 objectives. I didn't make them red to make them go away. I made them red to point out you still need to know how to do those 4 things. So if you have questions about either any of the content in this video or any of the content of those 4 objectives we didn't discuss, or any specific question from Sapling or anything, get in touch with me either by phone, by email, come to my office hours. Remember that we have an ACE tutoring center on campus, so a free tutoring center with a full-time, very qualified chemistry tutor, a part-time chemistry tutor, and student tutors. We also have the online tutoring Net Tutor. So please take advantage of your resources, and I hope you are having a great week 2.